We now want to talk about forming ions where we have some special cases.
Okay, so if we then kind of want to look at, there's some other parts of the periodic table where forming ions gets a little wonky. So if we look at gallium, for example, so its configuration, it has argon and then 4s2, 3d10, 4p1. So in order for it to become isoelectronic with the nearest noble gas, it has two possibilities. Either it loses all 13 of its valence electrons, looks like argon, which is pretty unlikely, or it fills up this shell. I'm sitting on one p-type electron, and it could gain 5 more to get full. Both of those are really big changes. That is too many electrons to either lose or gain. That is just not possible. Your noble gas configurations do tend to be stable, but there would just be a really high cost to removing 13 electrons, that it's not worth it. So what instead happens is the gallium forms an ion with what's called a pseudo noble gas configuration. So pseudo means it looks like, but not quite. Okay? So we can see that what happens with the gallium is if we go back to it, it has this open 4s2 and 4p1. And those subshells, those electrons are what are lost. So if it only loses those 3 electrons, now it's argon, where everything is full in argon, plus 3d10. And importantly, 3d10 is entirely full, and it corresponds to a full shell. The n equals 3 shell is now completely full. The s and p subshells that are contained within the argon part are now an octet. You don't have these non-octets up here. So pseudo-noble gas configuration always is going to look something like a noble gas part plus a full part of a full D-type subshell or a full F-type subshell, or both of those. This really doesn't happen very much in the periodic table. It really only happens with cations from the P block that's at gallium and above. So there's not many of them, but there's a handful of atoms that are following this pattern, and they're still predictable. So gallium is in column 3A. It tends to always form 3+. This is also how we can explain aluminum. Previously, we just said aluminum was 3. It does always form 3+ based on these noble gas ideas as well.
These pseudo-noble gas configurations only happen in metals in the P block that are after the transition metals. So right here is kind of the region you'd be looking at. Gallium was what we just looked at, indium, thallium, lead, tin. This is the area. It's not really a general property of anything else. It's just this handful, but it is kind of an exception that we can still understand using our ideas about electron configurations.
Our next complication is all of the transition metals. So if we remember when we learned about forming ions, we said transition metals was the Wild West. It just formed all sorts of crazy things. You couldn't predict what ion most of them will form. And the reason for that is they're doing kind of some odd business when it comes to removing electrons from those orbitals. So if we look at scandium, we would write it as scandium, the noble gas configuration. We got argon, 4s2, 3d1. And so if we're going to ionize these, we're going to form cations, we're going to take electrons out. Normally we would think we would start at the end here with the 3ds. But instead, we take electrons out of the 4s first. So whenever you're going to remove an electron, you always start by taking them out of the 4s. So scandium plus becomes 4s1, 3d1. So the 3d electron sticks around. So when you're going to take that first one out. If you're going to do scandium 2 plus, similarly, you still stick with taking out the s electron. Okay, so you take that out right there. And then if you want to take another one out to go to scandium 3 plus, now you finally take the d electron. So this is why these scandium or transition metals aren't as strict in which ions they form. Because if you look at all these, you're just taking out of s's or d's. There's all sorts of unfilled shells. It's kind of small differences between all of them as opposed to just hitting kind of that perfect pseudo-noble gas or noble gas. But we can look here, there is going to be a limit. We can, what about the next one? Could we form scandium 4+, right? Could we keep going? Could we take another one out? Well, now the answer to that question is going to be a hard no, because we can see with the scandium 3+, that looks like argon. So now when we go to take another electron, that would be taking it from something that's isoelectronic with a noble gas configuration. And that's never going to be a viable option. That's never going to work out for us.
Let's do some examples. Write the noble gas configuration of the most likely ion for each of the following metals. So one thing to key in on is now we're looking at metals. You'll note both of these sorts of odd situations, pseudo-noble gas transition metals. This only happens when we're talking about metals. These are the not fixed charge metals that we're talking about. When we want to do it, that question is what's the most likely ion? So the first step's always going to be figuring it out. You will note when we start to move into the transition metals like titanium, you may need to be told what the ion is because you can't, figure it out for yourself. Titanium forms more than one. There is no most likely ion. But for other things like thallium, Tl, and zinc, which is Zn, we can figure that out. And then, what's the change in electrons? The one complication being that we have these sorts of, issues when it comes to these pseudo-noble gases and when it comes to how we take out electrons from transition metals. But we can use those rules and still just remove or add electrons where we need to.
Tl is right here, thallium. Okay, so thallium is a little bit odd. We can see one of the things right away, it's kind of in, kind of a weird location on the periodic table. But if we look, it is in group 3A. It's a metal. It's going to lose electrons. It's going to form a cation, and it's going to lose 3. This is actually the same idea as we said. Aluminum always goes 3+. Gallium also goes 3+. So there's a lot of actually this whole column besides boron goes 3+. So if we look at thallium, we can see there's here. So 3+ means we're going to lose 3 electrons. Thallium has a lot more than 3 electrons on top of the xenon, right? That xenon core, and then it has 6s2, 4f, 5d, and 6p. It can't lose, it can't lose all of those. We need to just lose 3 of them. And so the question is, which 3 are going to be the easiest to lose? And it's going to correspond to those that are in this 6. Those are the furthest out, and importantly, not in complete shells. This 4F and 5D, those are full subshells. Those are buried down, right? They're in the lower shells. 4 is less than 5 and 6. That means it's literally closer to the nucleus. They're smaller. They're going to be staying in. So when we go to remove it, what we're left with is the xenon, 4F14, 5D10. This is a pseudo-noble gas configuration. Right? They're all full. The F's and the D's are all full on top of the xenon, where the S's and P's are all full. Importantly, you will note that in the Tl3+, there is no S or P subshell that is unfilled. So if we want to look at Ti, Ti is right here. Because it's a transition metal, you can't predict the charge, so you have to be told on these. And we can be told that this is Ti2+. So titanium 2 is what we can form here. And if we look at the electron configuration of titanium, argon is the preceding noble gas, Ar, 4s2, 3d2. And we are going to remove 2 electrons. And the thing to be mindful of is that whenever we're dealing with a transition metal, we always remove the s electrons first, even though we write them in the front there. When we go to ionize them, those get taken out preferentially. And then we end up with Ar, and the 3d2s are still sticking around. This is one of the reasons why so many transition metals form 2+ cations, because you just take only the s electrons and then you leave all the d's sitting in there. Again, there's just kind of a lot to do here. You can't really get a pseudo-noble gas in any way. That's why there's a lot of flexibility with removing electrons out of transition metals.
Zn is zinc. It's right here on the periodic table, and we'd see that. We normally think, hey, that's transition metal. We can't predict that. But if you remember, zinc was one of our special cases. Aluminum, zinc, and silver, right in a row, were metals where we could predict their charge. Zinc is always zinc 2+. So we know that zinc is always going to be zinc 2+. Zinc ions are just 2+. So if we look at zinc atoms, we can see, just like Ti earlier, argon is the preceding noble gas. It is up here, and then what we add onto it is the 4s2, and then we fill the entire D block, so that is 3d10. So when we go to ionize it, we know we're going to remove 2 electrons because it's Zn2+, and because it's a transition metal, we take out those s electrons, meaning we are left with argon and then the 3d10. So we can actually see here, previously zinc, we just said it is, right? Zinc just is 2+. We can understand now why zinc forms zinc 2+ only, because it's a pseudo-noble gas configuration. You have those 2 electrons in the 4s, you get rid of those, you got argon, and then a full subshell. So Zn2+ is argon with 10 electrons in that 3d subshell.